Welcome back. We have a new chapter, which means we have new vocabulary. So this chapter is going to be all about angles. So here we have two rays. These two rays are going to intersect at a point called the vertex, and we're going to say there's a direction here. So I'll declare one of these as the initial, we'll call it the initial side of the angle, and the place where we end is going to be the terminal side. And then the angle is going to measure the amount of rotation from initial side to terminal side. And then if I were to construct another angle, perhaps with a different orientation, as long as the amount of rotation is the same, we call those angles congruent. Cool, geometry. Now, in this chapter, we're going to discuss this thing called standard position. We're going to take our angles and preferentially, we're going to place them in the XY coordinate system so that the initial side shows up on the positive x-axis. Initial side. And the vertex right here. Okay, so if we put an angle like this, then we call it an angle in standard position. So then, if we were to have a counterclockwise rotation, so this would be the angle right here, we're going to call this a positive angle. But if we were to go clockwise instead, we would say this would be negative. And since we are in the x and y coordinate system, we have these ideas of quadrants. So quadrant 1, quadrant 2, quadrant 3, quadrant 4. And we can say that this angle terminates in quadrant 1. This angle terminates in quadrant 4. And then one last thing for vocab. If we have an angle that terminates on the y-axis, either positive or negative, or on the x-axis, positive or negative, we call those special angles quadrantal angles. You may never hear me use this phrase again, but it's a thing that it doesn't hurt to know. So for a while, we're going to be living in a world with a circle and an XY coordinate system. So our standard position angles are going to be with the initial side along the positive x-axis, and if the initial and the terminal side are in the same place, meaning I have not rotated anywhere, that would be a 0-degree angle. If I rotate 90 degrees counterclockwise, that would give me a 90-degree angle. If I keep going 180 degrees counterclockwise, that would put me on the negative x-axis. If I go 270 degrees counterclockwise, I would end up down here at the negative y-axis. And then if I go a full rotation around the circle and end up at the same place I started, I would have 360 degrees. So this raises an interesting point. In the case of 0 degrees, I went nowhere. In the case of 360 degrees, I did a full lap around the circle. But these ended up with the same terminal side. We call these coterminal angles. So coterminal angles have the same terminal side, which means they are 360 degrees or a multiple of 360 degrees apart. What we mean by this, what if I were to take 90 degrees and I add 360 degrees to that? That means I'm going to go to 90 degrees and then do another 360 degree lap around the circle, but I'm ending up at the same place. I would get 450 degrees, and the claim is that this and this are coterminal angles. But what if I did another lap? What if I did 90 degrees plus 2 times 360 degrees? Well, that's going to be 90 degrees plus 1 lap plus another lap, but same terminal side. So this would be 810 degrees, and this is also coterminal with those angles. Now what if I went clockwise? What if I said 90 degrees minus 360 degrees? So that means I would go to 90 degrees, but then go clockwise 360. Same terminal side. This is negative 207 degrees. And you can visualize this as start with 0, and then just go clockwise 270 degrees. You'll end up at the same place. What if I went clockwise 2 laps? Well, 90 degrees, then clockwise 1 lap, clockwise 2 laps. I end up at the same place. So 90 degrees minus 720 degrees is negative 630 degrees. All of these are coterminal with each other. There are, in fact, infinitely many such coterminal angles because I can make more just by adding 360 degrees or subtracting 360 degrees. In general, we say to get coterminal angles, we will often use the variable theta, the Greek letter like this, to indicate an angle measure. So we'll say theta is coterminal with all theta plus 360 degrees times n, where n is an integer, meaning n could be 0, plus or minus 1, plus or minus 2, plus or minus 3, so on and so on. So if you're a multiple, positive or negative multiple, of 360 degrees away from your original, then you are coterminal. So there are certain angles on the circle that are of great interest to us, and you'll see this kind of picture quite frequently. This isn't perfect, but you'll have to get used to my freehanding. So we have 0 degrees, 90 degrees, 180 degrees, and 270 degrees labeled. The next ones that we want to talk about are the ones that are halfway between the 0 and the 90 degrees. So this one will be 45 degrees, halfway between 90 degrees and 180 degrees. So this is 135 because it's 90 plus 45. And then halfway between these will be 180 degrees plus 45 degrees. And then halfway between these would be 270 degrees plus 45 degrees. And then the next ones that are labeled, these ones are the 30-degree increments. So first of all, this is 30 degrees, and then double of that, this is 60 degrees. Then 30 more degrees gets us to the 90 degree. 30 more gets us to 120 degrees. 30 more gets us to 150 degrees. And then 30 more gets us to 180 degrees. 30 more is 210 degrees. 30 more is 240 degrees. 30 more gets us to 270 degrees. And then 30 more is 300 degrees. 30 more is 330 degrees. And finally, the last 30-degree increment gets us back to a full circle of 360 degrees. All right, here on the screen, we have a circle with radius 1, and I have an initial side over here on the x-axis, and I have a terminal side over here. And we're going to do the calculator equivalent of using a protractor to measure this angle. So if I make a measurement with a directed angle, I can say this is the initial side, and you can notice that as I go around the circle, the angle measure is increasing as I go counterclockwise. And if I lock into the terminal side, I'm going to have this 198.02 degree angle. Now, what if I want to find angles that are coterminal with this 198.02 degree angle? Coterminal with... So we understand that we can add 360 degrees or subtract 360 degrees. So maybe the phrasing is going to be find the smallest two coterminal angles that are positive. Sure. What if I take 198.02 degrees and if I add 360 degrees? Well, that will just get me 578.02 degrees. That's coterminal. And I can instead take 198.02 degrees and add 360 times 2, which would then simply get me to 898.02 degrees. Great. Now what if I wanted to go clockwise to get negative values? 198.02 degrees minus 360 degrees, which should get me negative 161.98 degrees. And then if I wanted to go another 360 degrees clockwise, this should get me negative 521.98 degrees if I did the math right. Okay, so all of these are examples of coterminal angles, and once again, we have infinitely many of them. And perhaps we can visualize this by saying menu geometry, and then we'll take a directed angle measurement. So this will always take things counterclockwise because of the calculator settings I have. So I'm going to start with this over here, and I'm going to measure counterclockwise back to the positive x-axis. And so that 161.98 degrees, if I wanted to think about this in the normal direction of initial side backwards to the terminal side, I would think about this as a negative 161.98 degree angle. Okay. Now, there's perhaps a mildly entertaining thing we could do here, where we can say, what if I have something like 138.37 degrees? And for whatever reason, I decide today that I don't feel like having decimal values, which doesn't make much sense because decimals are awesome. But historically, there has been a thing called a minute of arc, which is classified as 1/60th of a degree, which means there are 60 minutes of arc in 1 degree, kind of like how there's 60 minutes in 1 hour. And by extension, there is a second of arc, which is 1/60th of a minute of arc. And so we'd say there are 60 seconds of arc in 1 minute of arc. Okay? And what we're going to do is we're going to take this and convert to DMS, which stands for degrees, minutes, and seconds. So the process behind this is we're going to take the 138, that whole number of degrees, and leave that alone. We're going to say 138 degrees. And then we're going to take the 0.37 fraction of a degree, and we're going to convert it to minutes by this conversion. So I'm going to take this and convert it 60 minutes for every 1 degree. Now, this is going to be 138 degrees plus, that should be 22.2 minutes. And then we're going to say, let's take this decimal number of minutes. So I'm going to chop that. I'll have 22 full minutes plus 0.2 leftover minutes. These are going to get converted to seconds by this conversion. 60 seconds of arc over 1 minute of arc. And so finally, I will have 138 degrees, 22 minutes, and this is going to be 12 seconds of arc. So we write it just like that. Instead of the pluses, we write it with no spaces. What if we want to do this conversion backwards? So let's say something like negative 217 degrees and 31 minutes and 22 seconds of arc, and we would like to convert this to decimal degrees. Well, the negative 217, that integer, that part's fine, and we're going to take the minutes and the seconds of arc and convert them back to degrees using these conversions over here. So we understand that it's 60 minutes is going to go to 1 degree, and 60 seconds is going to go to 1 minute, which means 3,600 seconds is going to go to 60 minutes, which is going to go to 1 degree. So this is going to be the conversion right here. All right, so we're going to say negative, I'm going to put the negative out front, 217 degrees plus 31 minutes of arc is going to get converted to 1 degree for every 60 minutes of arc, and the 22 minutes of arc is going to get converted to 1 degree for every 3,600 seconds of arc. Now if we put all this together, this is negative 217 degrees. This part is going to be plus 0.5, what did I do? I did 5167. I cheated and punched this into a calculator. And then plus this right here is going to be 0.0061, rounding to 4 decimal places. And if I put all of this together, I'm going to get negative 217.5228 degrees. And here I have it. Mildly entertaining. I mean, since we're using a calculator anyway, is there a way to just make the calculator do this whole conversion? Well, the answer is yes. And let's open a new page. Let's make a calculator page. And we'll type in 138.37 degrees. And to get a degree symbol, the 2 easiest ways, if you click the pi button in the lower left of your calculator, there's a degree symbol right here. Or if you click Control and then you click the catalog button, which is the little book icon, you get an expanded sort of list of symbols. And so I'm going to pick degrees right here. Then I'm going to go back to Control, then the catalog button, and I'm going to use this solid right arrow for convert. So I would like to convert this to DMS, degrees, minutes, and seconds. Boom. 138 degrees, 22 minutes, 12 seconds. Not so bad. And in fact, because I am in degree mode, if I were to type 138.37, this is by default in degrees. So even without the degree symbol, I can do this, DMS, and it will understand what I mean. Cool, same thing. Now let's do the opposite. So if I want to start with DMS and turn it into decimal degrees, so I need to be able to format in DMS first. If I hit the button next to the catalog, this brings up different input formats. So what if I click this, that was in the middle on the left, that's degrees, minutes, and seconds. So I can literally type in, with a negative out in front, 217 degrees, 31 minutes, and 22 seconds. And if I take this and go over here, do the Control catalog to bring up the solid right arrow for convert, DD is decimal degrees, negative 217.522, and I rounded the 4 decimal places. So this is what it is. Now, in fact, because I am in degree mode, it will convert everything to decimal degrees by default. So if I go up copy this down, and instead of putting that, I just hit enter on this. It understands that it needs to convert to decimal degrees to be in the default representation, so I will have that. Notice there's no degree symbol. When the calculator is just giving you a value in your mode, it won't bother putting the symbol there. So going forward, it's really important to make sure that this is the correct mode, and sometimes we will be in radians, sometimes we'll be in degrees, and you can click on it to switch back and forth, or you can go to document, and you can go to settings and statuses, and then document settings, and you can change this angle, radians, degrees, and we will not be using gradients. So back to the circle. Now we get to talk about arc length. And so standard position angles, let's have the initial side here, and let's put a terminal side somewhere around here. And so we have an angle measure of theta. And what we also want to label is this thing called the arc length, which is the curved segment that's a portion of the circumference. And obviously, because arc length starts with an S, we label it S. Well, circumference is 2 pi times the radius of the circle. So in this case, that would be r. And this is actually the original definition of pi, in the sense that if you take the circumference of a circle, divide by the diameter, then that comes out to be a constant ratio, and we called that value pi. So this is a definition statement. And then, perhaps I can convince you that if this angle is, let's say, 1/6 of 360 degrees, so if this is 60 degrees, then that should be 1/6 of the full circumference of the circle, right? If this angle is half of the circle, so 180 degrees, then the arc length should be half of the circumference. And it turns out that whatever this angle is, the fraction of the whole circle angle, so this fraction theta divided by 360 degrees, is the same as the arc length over the circumference. Okay, so generally speaking, we can say then the arc length is going to be written as 2 pi r multiplied by the angle out of 360 degrees. And this is a very useful tool. As an example, what if I say there is an angle theta equals, let's just go with 50 degrees, and then the radius r equals 8. Then I can immediately say the arc length, S, is equal 2 pi multiplied by r, which is 8. Take that multiplied by theta, which is 50 degrees, out of 360 degrees. And so this is going to be, I can reduce this is 180. And then 8 can be reduced down to 2, and this is going to be 45. And then this can be reduced to 10 and 9. So at the end of the day, it's going to be 20 pi over 9, which will be the length of the arc if the radius is 8 and the angle is 50 degrees. Okay, cool. Then, some really clever people came along and said, why do we need to measure angles in degrees? I mean, 360 is a nice number, but what if we came up with a nicer number? So it turns out a really nice number is 2 pi. So we're going to say, let's come up with a new unit to measure angles. So there's exactly 2 pi of that thing in a full circle. We're going to call it a radian. So the way it works is there are exactly 2 pi radians for every 360 degrees. Now you can think about this as like feet and inches, right? You would say 1 foot is equal to 12 inches, and they're the same thing, you're just using different units. So 2 pi radians is the same thing as 360 degrees, but we're just measuring in a different type of unit. Well, let's go ahead and reduce this. So pi radians is going to be 180 degrees, and we're going to use this as the conversion. And so let's consider circle, angle in standard position. We'll just say this is 60 degrees perhaps, and we would like to convert 60 degrees to radians. Well, the conversion, just like how we convert feet to inches and vice versa, we can say 60 degrees multiplied by, I want degrees on the bottom and radians on the top, and the conversion factor is 180 degrees for every pi radians. So the radians will be the final unit, the degrees will cancel. And I can simplify this by hand, that's 1/3. this becomes pi over 3 radians. And pi is a number. It has a decimal representation, 3.14159, so on forever. We can take this and approximate it by saying in the calculator, I will type in literal pi divided by 3, hit the button, that's a number, 1.047, I'll round to 4 decimal places, radians. So apparently 60 degrees is a little bit more than 1 radian. Well, what if I want to do a different conversion? Convert, let's just say like negative 139 degrees to radians. So that would be saying clockwise 139, so it'll go somewhere around there, negative 139 degrees. And the method is exactly the same. Negative 139 degrees multiplied by, I want degrees on the bottoms, radians on the top. It's 180 for every pi. This cancels that. And I don't feel like leaving it as negative 139 pi over 180, so I'll just turn it into a decimal. Right? I can say here, negative, boom, 139 times pi divided by 180. Hit the button, and I get negative 2.4260 radians. So that is almost 2.5 radians clockwise. Well, what if I want to do the reverse conversion? What if I want to say convert 3.98 radians to degrees? Well, I can say 3.98 radians multiplied by, I want radians on the bottom to cancel, and I want degrees on the top. So I'll put pi radians for every 180 degrees, and I can punch this into a calculator and say 3.98 multiplied by 180 for every pi. Hit the button. That is apparently 228.0, we'll go with 2 decimal places, 04 degrees. Okay. Now, there are also buttons you can push in the calculator to do this for you. For example, I can type in 3.98, and the radian button, if I hit Control in the catalog, is a little r. It's the upper right thing. That means 3.98 radians. And I can take this and I can convert it, as always, to decimal degrees. And I get that button. Or, noting that I'm in degree mode, I could delete that and say, just give me the value in whatever mode I'm in, and that will be 228.04. Now, what if I change this to radians? Okay. Now, then if I type in 3.98, this is just in radians. And if I type in 3.98 and I want to convert this into degrees, right, I can actually drop the r because I'm already in radian mode, and it'll give it to me in degrees. What if I want to do something up here where I want to convert 60 degrees into radians? So if I just type in 60, okay, I'm in radian mode, so this is 60 radians. So I need to correct that. I need to make sure I'm in 60 degrees, and I'm going to convert this to radians. So I can do it one way. I can use the arrow, and I'm going to say RAD. It turned it into 1.0472 radians, just like we expected. But I could also do this where I delete the radian part and just say 60 degrees, but since I'm in radian mode, please express this in the mode I'm in. Boom. It just gives me the thing in radians. So these distinctions, do you have to understand them fully? No, but it's good to understand that they are there and to play around with your calculator to make sure you understand what you're getting when you punch in these various things. So the final conclusion is actually very cool. So when you have a circle and you have a certain angle theta, and let's just imagine this theta is even bigger than 90 degrees. So let's go over here, this angle theta. And you have an arc length out here, S for arc length. Then we understand that there is an equation for arc length that we derived logically. S is equal to 2 pi r multiplied by theta in degrees out of 360 degrees. It's the part out of the whole. Okay? But if we choose to measure theta in radians instead of degrees, we'd say S is equal to 2 pi r times theta in radians over 2 pi radians. So then we'd say this 2 pi and this 2 pi cancel, and you get a much simpler equation that the arc length is just r times theta in radians. So that means if theta happens to be exactly 1 radian, then the arc length and the radius are the same as each other. So in fact, this is often how we teach what a radian is. We say a radian is the magical angle where the arc length is the same as the radius. And so the conversion is radians to degrees. We know it's 2 pi radians for every 360 degrees, which means it's pi radians for every 180 degrees. So what if we ask the question, what is 1 radian? Well, let's ask the calculator. We can say 1 radian converted to degrees. So we are default in radians, but just to be super clear, let's slap this up here, 1 radian, and let's convert this to decimal degrees. Turns out it is 57 point, and I'm only going to put 2 decimal places, 57.30 degrees. So a little bit less than 60, perhaps right about there, that would be the magical angle where the arc length is exactly equal to the radius. And just to be clear, right, let's imagine you have a calculator that doesn't do these things, and you would want to do this conversion by hand. You would say 1 radian multiplied by, you put radians on the bottom, degrees on the top. It's for every pi radians, there are 180 degrees. And you would say here 1 times 180 divided by the number pi, and that would be the exact same thing. 57.30 degrees. So we have radians, we have conversion, and most importantly, we have this equation for arc length. That will be our friend. And I think that's all we need to cover today. Thanks for tuning in. I'll see you next time.